So up to now we've spent all our energy on understanding the consequences of conformal symmetry on classical and quantum systems, and haven't yet really focused on any examples. So there's always the possibility when talking about constraints of some structures that there may not exist a structure apart from the trivial one that obeys those constraints. So today we're going to deal with that problem and present the first example, and in this course only example, of a conformal field theory. Now, this may seem to be a gross omission to only focus on one example, but between this and another example, the free fermion, you actually capture quite a lot of what we know of in terms of constructive examples of conformal field theory. It turns out using the free boson and copies of the free boson and various constructions, you can construct all kinds of other conformal field theories. So we don't actually lose very much in studying this one particular example in great depth. So the free boson is, well, it is what it says, right? The Lagrangian of the free boson is that of the Klein-Gordon field. So it's that. Now you might expect me to write that when I say the action of the Klein-Gordon field, but that's not conformally invariant. The mass here, m, the mass term, I should say, induces a length scale, and this is no longer a conformally invariant system. So in fact, the only chance for a Klein-Gordon field to be conformally invariant is if this m parameter is 0. So we wipe it off, and now we already have the action for the free boson. So nothing could be simpler, right? This is the easiest theory. Since we've solved the Klein-Gordon equation in our quantum field theory course, we've already solved this equation, solved the dynamics. We've already solved the dynamics for this field. That's true, and in some sense, everything we do today will just be a review of a solution that you've already looked at already. Now, we're going to specialize to 1 + 1 dimensions. That's the setting. In fact, we'll actually be doing things mostly in the Euclidean picture, so we'll be specializing to 2 + 0 dimensions. And we'll just briskly run through the solution of the Klein-Gordon free boson in 2 + 0 dimensions via the path integral, just to remind you. And along the way, we're going to discover a couple of interesting quirky features of this theory. Typically, when you studied Klein-Gordon in the past, you've always had this mass term, and this mass term introduces a length scale, and the correlation functions are decaying, etc., etc. By turning this off, I mean, technically, everything you've done before has included that analysis where m is 0, but actually, there are some edge cases that we have to look at when m is 0, which will drastically change the physics of this model, and you may not be entirely aware of that change. So the action which we need to do path integral quantization, I'll just write it like this for the moment, and then we're going to slowly manipulate this into complex coordinates. I think it's a plus, yes. So this is you can rewrite the action by integrating by parts and so on into this form and introducing the imaginary number I. We've just got this constant factor g over 2 here as for convenience. It plays no role in the classical dynamics, but it does play a role, or could potentially play a role in the quantum dynamics when you put this into path integral. So you can check just by substituting that in here and expanding and integrating by parts that you'll get the right answer. Now, dx underline here just means dx dy. So far, nothing too controversial. Now, we're going to write the action in a slightly more suggestive way for path integral quantization. Going to write it like a quadratic form, so like a sort of a matrix, a vector matrix vector equation. because that really helps when you can write the action in that form. That really helps with path integral quantization, because now it looks exactly like a Gaussian, and we know what to do with Gaussians and path integrals. So there, and then, so now we only have to wonder what is A in this case to make these things equal. So if you integrate by parts, then A is a differential operator, it's not a matrix. Let's see if I get my minus signs correct. So A just happens to be that differential operator here.
I'm sorry?
Yeah.
And do we integrate over 2 iterates now? Or
Yeah, okay, so the notation isn't optimal. The question is, are we integrating over 2? We are. So this is...
Is it the same integral?
yeah, the notation's poor. I will try and save the situation now by doing noughts and ones. So this is naught, this is 1, this is naught, this is 1. And now we've got x underline and y underline, meaning, right, x underline is x naught, x1, and y underline is y naught, y1. So we've got 4 integrals now instead of 2. All right. So now we rewrite the action as like a matrix, a vector matrix vector. And then we're going to substitute that into a path integral to quantize this theory. So when you have a path integral to quantize a theory, you've got to integrate over the field, configurations e to the is, but we're doing things in the Euclidean picture, so we have a minus here. And then to actually get correlation functions, you have to put the fields in. And then you have to take a limit, right? There's the limit as t, or in this case beta, tends to infinity. Sorry, 0, I believe. Now, we can go through and do a lot of calculations like that, but we know that it's convenient to use the generating functional when you've got a quadratic action, depends quadratically on the field. It's far better to use the generating functional to do all your calculations, because that tells you all these endpoint correlation functions for free. You just have to differentiate instead of integrate. So the generating functional, just to remind you, depends on a current field J and is defined, not defined, is actually given by this expression here. Defined by this expression here. So the generating functional depends on this external field J and is defined by this expression here. And as I hope you recall from the advanced quantum field theory course, to compute, say, some correlation function, it's sufficient to just differentiate with respect to J. and that brings down powers of phi into the path integral, and then you set j as naught, and then you can work out correlation functions that way. Now, because this is quadratic, we can actually work out the generating functional. Here it is. We just need to know what is k. K is the Green's function for this differential operator here. So that's just a little complete the squares trick. This is by far the most satisfying way, I know, to quantize the free boson. It even feels reasonably rigorous when you do this, completing the squares to compute the generating function. So and you get this extremely satisfying connection to the Green's function straight away, right? Instead of this somewhat indirect way when you do canonical quantization, work out the propagator and then notice that it's the Green's function for this differential operator. So there it is, that's the definition of k. So what is k? Well, it depends, right? It depends on the dimension, and it depends on whether or not there's a mass term. We have a no mass term, and we're in dimension 2. And so the Green's function for this wave operator in dimension 2, or this is actually now the Laplacian because we're in Euclidean space, is very interesting. It's one of the most interesting Green's functions that you can have. It's not behaves in a somewhat funny way, right? So you can just go ahead and check this, or if you're feeling game, you can do the Fourier transform or whatever to work out this Green's function. And the answer is, oops, a minus sign, this very striking function there, namely the log. So you know this is just electrostatics in two dimensions. You know that if you have a point charge, that the electrostatic potential behaves as a log. Now this is very, very strange actually. Just think for a moment, pause for a moment, how strange this function actually is relative to the case in higher dimensions. So in higher dimensions, when you work out the Green's function, it's not a log here, it's just like 1 over r, right? 2 plus 1. And 1 over r decays with separation. But here, just take a look at this, right? If you, it's x minus y all squared. If you take a look at the behavior of k with respect to separation between these 2 points, it doesn't decay, it grows. Now that is some strange stuff, right? That has some really strange consequences for the quantum theory that most, I'd say even most experts in many-body theory forget or are perhaps not completely aware of. So I'll tell you the consequences in a moment of this very striking result. How will you prove it? Well, as I said, you could go ahead and Fourier transform if you want and solve the inverse Fourier transform, Laplace transform, whatever your favorite transform method, or you could just substitute this in here and check that you get the delta function. Now, it's sort of convenient to rewrite this, which we'll do in a moment. But now, in fact, before that, I'll point out this very striking consequence of this result. This is a really excellent counterexample to a piece of intuition that most people in many-body theory have. So here's the consequence. So you do the path integral quantization. We now know the generating functional that has this log in here, and it's all good. And then we work out the 2-point correlation function. This is the quantum 2-point correlation function. Now, you can do it by the canonical quantization if you want. You can do it on the lattice and take the continuum limit. They all give the same answer. And the answer is, well, we'll do it today just by the path integral prescription. Oops, Zj, of course. Go through, work out those functional derivatives. That brings down 2 fields, phi1 and phi2 up there in the path integral, calculate, and then out comes the only answer that can come, which is kx comma y. Boom. Now that is some peculiar result right there, because if you were to ask a practitioner in many-body theory, quantum many-body theory, about the correlations in the ground state, and this is a ground state correlation function, of two local observables, and you'd ask them, how does that depend on the separation between those two observables, then I bet you 99% of the time, everyone would answer that the two-point correlation function decays with separation. Whatever, 1 dimension, 2 dimensions, 3 dimensions. No one would ever say, nearly no one, people who do remember this example will of course not say it, but the idea that a locally interacting system has ground state correlation functions that grow with separation is extremely counterintuitive. It goes against our intuition concerning locality. So this is just the result of extremely strange counterintuitive nature, right? We have a local system, it's a locally interacting field, we wiggle it somewhere, and we wiggle it somewhere else, and the further away you get, the stronger the correlation. Like, what's going on with that? It defies intuition, right? But it's what it is. So it's a useful example to keep in mind for this precise reason, that almost all intuition is based on this idea that correlations decay with separation. Here's one where it actually grows. And you always should keep counterexamples in mind, and that's the best one that I know. So we can rewrite this slightly just to make it clear that really we are the decay behavior, the growth behavior with separation, just writing it in polar coords. But it's sort of stupid to have square roots, so what we typically do is this. So that just, makes things a little bit more, a little bit less awkward when it comes to going to complex coordinates. Now, we make the sort of the first big extrapolative step that we always make in conformal field theory, which is we analytically continue. So up to this point, this theory has been defined in real Euclidean space. No complex numbers, nothing like that. These x's and y's are labels for events in a Euclidean space-time. And we've not said that they can be complex, and we haven't asked that our theory be defined for complex values of those space-time locations. And there's no reason to believe that we can analytically continue. Why should this even make sense to allow x and y to be complex numbers? Physically, it's already questionable. But the correlation functions of a theory can sometimes allow you to do it, and it's sometimes a helpful thing to do, right? Just as it is when solving equations, you have some polynomial equation in real numbers and it has no solution. Well, sure, yeah, it's defined over the real numbers, but you can also make sense of that equation over a bigger field of complex numbers and find solutions. And so it doesn't mean that those solutions are physical, like that they don't cross the x-axis, but they tell you important information about the equation. Exactly the same here. We're taking these correlation functions, which are only physically defined when x and y are real, and we're going to say, let's just take them and look at them just as mathematical functions and analytically continue to complex argument and see what it tells us. And, well, we know that log is one of those functions that you're allowed to analytically continue. I mean, it might have been that we had this correlation function wasn't a log, that it was some function that can't be analytically continued. That could have been, but it isn't the case. So we're allowed to analytically continue, so why not? Let's do it. So we define complex coordinates now. oops, x0 plus I x1, yep. And actually we do that, and it's only when we introduce really the complex conjugate variables and make them independent that we've truly analytically continued this function, but that's just... So now we can ask, well, what if we interpret those locations x and y as now complex numbers? What's the behavior? Well, everything, right? We have to express everything now in terms of z's and w's. And when you do, you get, I'll save you the bother of doing that. You get this answer there. And it's a log of a product, so we can turn that into a sum of the logs. And that clearly shows its dependence on the anti-holomorphic and the holomorphic parts. So it's really only at this moment that we have done any analytic continuation at all. Just by interpreting points in Euclidean space as points in the complex space isn't analytical continuation. It's only when you introduce z and z bar and make them independent that you've actually analytically continued. That's what we've done on that line there. So now we're going to try and interpret what we have here as a conformal field theory. So we've got the two-point correlation function. Because this is a Gaussian theory, Wicks' theorem gives us all the rest, right? So we don't have to work particularly any harder to get higher order correlation functions. We just use Wicks' theorem, and that will allow us to express all of them in terms of this two-point function here. Yeah, there's some annoying combinatorics, but that's more or less settled. So now we want to interpret this as a conformal field theory. Is it a conformal field theory? And the answer is actually not obviously. And the problem is that phi of z is not a primary field. Just behaves the wrong way, right? Look at the two-point function. The two-point function, as I stressed earlier, grows with separation, behaves as a log. But if you have a primary field, we already know what the two-point function of a primary field must look like. It must look like 1 over something, 1 over a function of separation, and this does not look like that. So at least as we've defined it, it's not a primary field. And what to make of this? Well, the answer that we're going to pursue is that this is a theory with lots and lots of observables, and we just happen to have written down observables that aren't particularly well behaved. So phi, which we've chosen to think of as our fundamental observable, has this particular behavior, but there's no reason that that's the only observable that this theory gives you predictions for. You can write down other observables, and you could look at a subset of the observables that do behave in the way you want. It's perfectly allowed. It's perfectly allowed to neglect observables and look at the remaining ones. And to that end, we can find a candidate for a primary field. We just introduce this observable here. We differentiate the argument of phi, differentiate with respect to the argument z, and we have a new operator, dz of phi hat of z, and turns out that actually is a primary field because it behaves in precisely the way a primary field has to behave. So if you try and work out the 2-point function of this local observable here, you do get something perfectly consistent now with conformal invariance. And it's super easy to work out this correlation function. You just go over here, you differentiate with respect to z, and you differentiate with respect to w, and you get a nice answer. And it's beautifully holomorphic. And so we have found a nice candidate primary field. I guess I'll put bars over them for the anti-holomorphic. No. So that's perfect. That's exactly how primary fields behave at dimension 1. Right? H is 1. And so we can write the OPE for the field dz of phi, just taking this expression here and using this notation that we've introduced, and the answer is that the OPE behaves like this for the candidate primary field. We don't actually know it's a primary field yet because we haven't seen how it transforms under conformal transformations yet, so it's just consistent with it being a primary field. So to actually check if an observable is a primary field, you need to see how it transforms under conformal transformations. And for that, in turn, you need the stress energy tensor T mu nu. Well, actually, we really want T hat Z, which we've defined in terms of T mu nu. Now, it's usually a very difficult task to construct the stress energy tensor because that's the generator of translations in time, space, dilations, everything. And that means you completely solved your theory once you know the stress energy tensor. Well, we're lucky, well, because it's Gaussian and quadratic and we have the path integral, we can actually work out the exact form of the stress energy tensor. So let's start right back to the definition of the stress energy tensor for a quadratic theory. And one way of understanding the stress energy tensor is the μth component of the momentum flux of the μth component through the μth coordinate constant plane. That's what the one interpretation of the stress tensor is. Another is that it's the conserved charge corresponding to a translation in the μth direction, or the μth direction, it's symmetric. And another one is the variation of the action with respect to the metric. That's another one that I didn't actually talk about in this course. So you can take the action and then vary with respect to the metric. That also gives you an expression which is a stress energy tensor. They can differ, and in fact there's some annoying issues to do with traces that we have definitely skipped in this course. In this case we have an expression. I will save you the bother of rederiving it from Noether's theorem. So for the Klein-Gordon field, it's this expression, and then you put in here the Lagrangian in there. That's how you derive the stress tensor. But for us, this is actually pretty easy, so we'll just write it so. So you take your favorite method to getting this. Make sure it's traceless, right? We need to ensure that we have a traceless stress energy tensor. And once we've got it, we're going to quantize, right? So how do you quantize a quadratic theory? Well, you're always in luck with quadratic theories. Putting hats on is a perfectly legitimate way to quantize, and that's what we'll do here. The only thing left to do is to find this T hat of Z, and that's this. So I didn't really find a kind of neat way to do this. Bit of a shame somehow. You take the ZZ component of this tensor, so you have to so the steps involved, right, to getting T hat of Z, is you take this stress energy tensor here. You change coordinates from x0, x0, x1 to zz bar, so that's a coordinate transformation. You then find the zz component of this T hat, and it has a not particularly easy to remember form. Sort of a bit of a shame. I'll write it out. There's the 0, 0 component minus 2i, the 1, 0 component minus the 1, 1 component. You can work it out. It's not very difficult or anything. It's just not particularly intuitive to remember this combination of ones and noughts and so on. And then you work through the intermediate details, ... which is an exercise for you in just transforming or substituting this into this. It's really not very much to it. And then you come out with a rather intuitive, nice answer. So, couldn't be nicer, really. Except I've made one. I was premature in putting the hats on because of a certain issue. So please erase the hats. This is all classical. And then I'll explain what that one little nasty issue is that I neglected. Okay. So almost right about saying that you quantize things by putting hats on them, except sometimes you have normal ordering issues. And this is exactly one of those times right here. It should have been clear right from this line that there were going to be issues with normal ordering. Right? So if you write phi, if phi is a quantum field, then it's going to be written in terms of annihilation and creation operators, and hopefully you have some distant memory of how phi looks for the Klein-Gordon field, e to the I x dot p's and a p's and a dagger p's and so on. And so this particular combination here has got, you know, a p's and a dagger p's in it. Same here. But these are going to give infinite shifts. So, and same here, same problem here. So when you put hats on quadratic expressions like this, you have to normally order them in quantum theory. Just subtract off the infinite shift. So that's the only subtlety that you have to be a bit careful about. Just normal order that expression. So that's the colon notation for normal ordering. I think in my previous course I just used big N. Just subtract off the infinite energy shifts. So you can do all of this, what I've just said, in the case of the free fermion as well. You can play exactly the same game, and you'll arrive at similar-ish expressions, but with factors of 2 and things that weren't present in the bosonic version. I won't cover the free fermion in this course, but it is an extremely important example in conformal field theory. You should definitely go ahead and look up the solution of the free fermion, but there aren't really that many surprises apart from remembering to use anti-commutators instead of commutators, and there's a factor of a half. As we'll and between the free fermion and the free boson, you capture a lot of physics in critical systems, actually. There's not much that really of common occurring phase transitions that don't get well modeled by the free boson or the free fermion. Right, so that's the stress energy tensor. It's a pretty simple expression, a not so intuitive beginning, but it ends up very nice looking in the end. And now we can compute to check if this dz of phi really is a primary field. We can do the business now of computing the OPE of the primary field with the stress energy tensor. Oh, dz. Now I've done this 3 different ways over the years. Done it by canonical quantization, I've done it by regularizing on the lattice, and today we're doing it by this. And they all give the same answers, as they should for Gaussian theories. And the only real difficulty is keeping track of the notation and what's being done here. So what's being done here is just to be not get confused. So what we're doing here is we're saying, let's take the field operator for the stress energy tensor, Tz, and it's going to be W's. and compute a 2-point correlation function inside the ground state, look at its asymptotic behavior, drop the regular part. So that's what this notation means. It's actually slightly more involved than that. Maybe I'll write it all out in words, actually. Actually, what's being said here is you put this pair inside an endpoint function. Compute its singular behavior as z goes to w, and drop the regular part. So that's what this twiddle means. So it's a very simple looking notation for quite a complex sequence of steps. And because of Wicks' theorem, we can do this. Wicks' theorem makes this pretty easy to carry out these steps. But in general, it's not so easy. If we have a fully interacting crazy theory where the correlation functions are very, the higher order correlation functions are very difficult, then doing these steps could be potentially quite challenging. But Wicks' theorem allows us to do this relatively easily. So putting this inside a general endpoint function and using Wicks' theorem means that we can really focus on the behavior of z and w with respect to z and, oh, it should be w, sorry. Can apply Wicks' theorem and look at all the contractions, and we can really isolate the behavior of the correlation function on z and w, neglecting the behavior on all the other positions. So Wicks' theorem allows us to do the next step, which is minus 2 pi g. We have this normal ordered expression. Is that dz? Yep. And we have to contract that guy for that one. And then we have to also do the contraction of this one with that one, but we just factor that in by adding a factor of 2. Oh no. I really am doing it separately here. So just to stress that I've compacted very many steps into this one line here, and that if you're uncomfortable with this, it's probably better to rewrite everything in terms of annihilation and creation operators, and then do this actual manipulation here at the level of annihilation and creation operators. You'll get the same answer, but you'll probably feel better about it. Now, the contraction of z and dz phi hat and dw phi hat, that's just the 2-point function, it's the Feynman propagator, and so we can write out the answer in fairly short order. And we know what this thing is here. That's 1 on z minus w squared. But we're not quite done yet. Because it's not entirely exactly in the right form of an OPE. For this to be in the form of an OPE, we have to express this as a Taylor series around W. So this field operator is around Z at the moment, but the OPE needs that this is around W. So we do a Taylor expansion. To get this field around W instead of Z. And then we end up with our final answer. Because these higher terms here, are regular, they no longer depend singularly with the separation, but in fact regularly with separation, they get neglected when we use this notation. So we're just left with 2 terms. And that is exactly how a primary field with H is 1 behaves. Under an infinitesimal conformal transformation. So we found a family of observables which get to be called primary fields. We found a family of observables called the stress energy tensor. That's the data we need to build up this conformal field theory. That is the data of a conformal field theory. But wait, there's more. And there's something very, very interesting now about the stress energy tensor. This is something, this is a calculation that you can imagine doing. So the calculation is as follows. Let's work out the OPE of the stress energy tensor with itself. So what this physically corresponds to is we do a local conformal transformation, then we do another one, roughly speaking. So that tells us if the product of 2 local conformal transformations, what is it as a local conformal transformation? This is going to isolate out that behavior. Well, the equations to do this are exactly the same as before. I mean, there's some extra contractions you need to do, but you're not going to need any new ideas or tricks to be able to do this computation. We write out the stress energy tensor. Now we have to use Wicks theorem and contract it. Blah, 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 Wicks theorem. I'll leave the details of that calculation to you. And then we get this very interesting answer. As before, we also have to tailor, expand this. To get it around W. And that's finally the answer for the OPE of the stress energy tensor with itself. Now that's almost, but not quite, the OPE of a primary field of H is 2. So the problem is that term, problem if you like, but it's not really a problem. This is a fundamental feature of quantum conformal field theories. There's an extra term relative to what we would have expected from the transformation law of a primary field of H is 2. Got this funny looking term here. And that term, which spoils it being a primary field, actually labels the representation of the conformal group that this theory gives us. And that label is given by this number here, the number 1, which we call C in general. So let's just write out what this looks like in general, and then I'll spend a moment explaining that point. So this is just done for the free boson. Now let's talk about what do we expect the OPE of the stress energy tensor with itself to look like in general. So suppose you have your favorite conformal field theory. We know there's at least one now, the free boson, but you have another one, and you ask what's the OPE of the stress energy tensor with itself. This is crucial for saying how do conformal transformations act, what algebra do they form. Even if I do one then another, how is that expressed as a conformal transformation again? Right? Here is how. That's what the OPE tells us. And you can ask, well, what is the most general OPE that we could write out? The answer is, you've got to have, well, you don't have to, but it's certainly allowed to have a term like this. The most singular part of the OPE in general has a fourth order power. That comes from the fact that the stress energy tensor is a tensor of rank 2. So under dilations, the stress energy tensor transforms like that because it's just a tensor of rank 2. That's what the tensor transformation law tells us. Oops, I got the z on the wrong place. Did I? No? So 1 on lambda squared lambda z. Yeah, I think that's correct. So any symmetric type 2 common naught tensor under dilations behaves like this. Hence, it's certainly allowed in the OPE to have a term that goes as z minus w to the 4. You can't have any more singular terms. And the coefficient in the OPE has to be proportional to the identity. Then the next term you can have, you might think that there's a third power that you could have, right? You know, why not that? Why not having some operator A of Z or A of W that over that? That can't be, right? Because this is, just think of interchanging Z and W. That would be anti-symmetric up here. Sorry, this is anti-symmetric here, but this is symmetric there. So you can't have a third order term. So then the next order that you can have is a second order term, and then the scalings require that we have at least one t, yeah?
Yeah, but this argument doesn't hold for the first term, isn't it? The first term is also the third term with order 1 because it's antisymmetric.
This is actually antisymmetric under exchange as well, dw, right? If you let w go to minus w, then you get a minus sign here, and then you flip it there as well.
So why couldn't we get antisymmetric A of W?
Yeah, okay, that's true. I can't see it for the moment why that term is forbidden. Certainly if you're only allowing functions of t of z in there, because we expect this to close, right? We expect that doing two conformal transformations is again an example of a conformal transformation, then we should be able to express the OPE as some combination of things involving the stress energy tensor. And then you're very limited about what you can put here. You can either put t of z there or dw of t of z there, and then the only difficulty is to explain why we don't have a dw of t of z there. I can't see for the moment why that's forbidden. Yep, I can't see for the moment why that's forbidden, but it is forbidden, I know. So we just have to accept that fact for the moment, unless I find a better argument in the sequel. All right, so that's what the general OPE of the stress energy tensor with itself looks like. And you have this sort of optional constant here. Now this corresponds to, it sort of looks very innocuous, it turns out that this constant C is coming from a central extension of the Witt algebra, which is just a fancy way of saying we allow the conformal group to act not unitarily, but projectively unitarily. So we'll see in the following derivations that allowing the conformal group to act projectively will introduce an additional phase degree of freedom that you can have, and that phase degree of freedom will correspond precisely to this 1 over z minus w to the 4 term. And it turns out C has to be positive, otherwise we don't have a unitary representation after you undo all the Wicks transforms and everything. And that you can sort of see rapidly, intuitively, by taking a vacuum expectation value. This should be greater than 0, right? Because it's got to do with the fact that T is the energy. Interpretation is the energy, translation in time. And then you can see that the most singular behavior here, in order for that to be positive, it better be that C is positive. So this is the sort of OPE in general. If you work out your favorite conformal field theory, if you have the power of doing so, and then you work out the OPE of the stress energy tensor with itself, the claim is it will always look like this, and there will be this number C over there called the central charge. What I want to do now is relate this OPE to algebra, a Lie algebra obeyed by certain generators, and those generators will identify with the generators of local conformal transformations. So that brings us to the final topic of this course. We're going to build an algebra, a Lie algebra, an infinite dimensional Lie algebra of the generators of local conformal transformations and work out their Lie bracket. That's the final objective for the course. And then we will identify that as a central extension of the Witt algebra, which is another way of saying it's just a projective representation of the conformal group. So the way to do this is we identify T of Z, we take its Fourier series, and then we look at the Fourier coefficients, and they all just end up being the generators we want. I think it's minus n plus 2, minus 2. It's just a definition, right? You're free to define operators Ln hat by taking a Fourier series. Laurent series. It's also a Fourier series if you restrict Z to be on the circuit, the unit circle.
Yeah, of course.
Yeah. So okay. Yeah, it's a Laurent series. I should use standard terminology. I'm thinking on the unit circle. So this is only defined in an annulus, right? There's got singular behavior here. It can go very badly wrong near the origin and also at infinity. And then as soon as you define something in an annulus, it's sort of convenient to find one point inside the annulus. Why not the unit circle? And then it's a Fourier series. So it's just a definition of these operators L hat, if you like. So we can, one thing we can do is invert that relation to find out what does L hat n equal in terms of T hat. Multiply by z to the power n plus 1 and integrate around a circle. That's how you get L n hat. And then the residue theorem gives you the rest. Just do that. So just invert that relationship, use the residue theorem, and we already have the definition now of the LNs and the LN bars in terms of our stress energy tensor. I've forgotten some bars, sorry.
Do we integrate over the anti-clockwise?
No, the clockwise.
And shouldn't then be that dz should be dz bar in the second?
Thank you, yes. The z should be a z bar here, that's right. Now, our goal is to work out if these operators, if they close to form some kind of Lie algebra, which would mean that they are a legitimate representation of some symmetries on our system. So we want to compute, therefore, the commutator of two of these things. And hopefully it's a linear combination of the LNs themselves. And if so, that would be a Lie algebra. And then we would have a group of an algebra of operators which generate symmetries, and we would finally conclude that our system is a quantum manifestation of the conformal symmetries, or gives a quantum manifestation. So in order to do that, we need to compute a commutator, right? Well, that's not entirely trivial. In fact, a little bit complicated, and to carry out this, we're going to need to use a contour integral trick that we introduced a couple of lectures ago. So you can realize a commutator by doing two contour integrals. Oops, that's a W and a Z, yeah, it's all good. So you can realize a commutator by doing contour integrals around a very special contour. This is super useful when you combine it with the OPE. So this is a really crucial observation. And it shows us why this apparently wasteful neglect of all the terms in the OPE. I mean, the OPE you have just 3 terms left, but that's not true, right? That's not what the behavior of Tz times Tw is. These two operators don't just combine to give exactly 3 terms, they give plus an infinite number of regular terms. You even saw that when I Taylor expanded. So what, have we lost anything in neglecting those? And it turns out we exactly don't lose anything when we compute this commutator, because these are the only 3 terms which will contribute to this commutator here. And I'll give you the argument now in terms of contours. So there's nothing wasted. We haven't lost any information after all. So I've already given you this argument before, but I'll just repeat it, so for completeness. So suppose you have 2 operators A and B, and they themselves happen to be contour integrals of some density around some contour. Then you can work out the commutator by doing this peculiar contour integral there. I'll explain those 2 contours now. So you've seen this before. Here's the origin, here's the point W. And then we do an integral around this contour, that's this one here. So just look at this particular set of contours here. If I integrate around a circle, around the origin, and include W and subtract from it the excluding W, this is Z here, then that's exactly the same as just doing a very tight little contour around W with respect to Z. So to do this, to observe this fact here, we're going to use this fact like an infinite number of times. So to do this commutator, we imagine fixing W, and then we do the 2 contours required to get the commutator. That's the commutator right there. And then we observe, but that's just the same as doing a tight little contour around Z, around W of Z. And then, since we fixed W, we then just have to repeat this for all values of W. And as you can see, that perfectly fits together with the OPE, because a contour integral around W will just pick up the singular behavior as Z goes to W, and all that regular behavior that we neglected just goes to 0. So now we can finally do this promised calculation here, ln Lm. Squared, right? And there's all the regular stuff, but that's going to go away to 0. So let's take a look at these terms in turn. What we're just doing here is residue calculus. Remember, we only get a residue when this overall factor here scales as 1 over z, or in this case, 1 over z. So computing the residue at that point gives you this funny number here. Computing the residue at this point gives you that funny number there, and similarly there. So the residue is z as it goes to w. And then you can start to expand and do the integrals over w now. And there things simplify quite a lot, because we no longer have such complicated terms. We just pick up a delta function in the first one. In the second term, we also pick up an easy factor by just recalling the definition of the L operator. And then we have a final contour integral to mess out. And we arrive here at the final answer.
I'm sorry,
yep.
You have written in the second line that your derivative over t omega is over z. So
oh, thank you. It's a w. You get exact same answer for ln bars. And you also get 0 for ln commutators with lm bars. So that's the answer to the question, do these operators close to form an algebra? And the answer is yes. It's an infinite dimensional Lie algebra, so we don't have a finite number of these operators ln here. We have an infinite number, one for every integer. And it's not just a simple Lie algebra. That would be the only term we could expect in a normal Lie algebra. We can't expect some combination of the generators themselves. But here we have an additional term proportional to the identity that arises. That's got the form of something called a central extension of this Lie algebra, which corresponds in turn to the fact that we have a representation of this Lie algebra here, the one where there's that term without, but it's a projective representation. This is the phase factor coming from the projective representation. That's not an obvious statement, but it's the case here. And this algebra has a name. It's called the Virasoro algebra. It's an infinite dimensional Lie algebra. It contains a closed subalgebra formed by L minus 1, L naught, and L1. And that's proportional to the SL2C algebra. We'll talk about that in the next lecture. And this is the algebra of local conformal transformations. And the global conformal transformations correspond to these three-dimensional subalgebra, or rank 1 subalgebra. But that's what I want to talk about for today. And in the final lecture, we'll explore the consequences of this algebra lying inside our conformal theories. We'll maybe say some words about representation theory of this algebra, and yeah, I'll discuss sort of future directions from here. Okay, but for now, thank you very much.